Okay, again, I am skipping over some lectures. This is a continuation of the last lecture we talked about, where we started talking about the brachial plexus. Now we're going to look at how neurons work. So in terms of nervous tissue in your body, it can be broken down into two parts. Your central nervous system, which we've been talking about up until this point, which is your brain and spinal cord, and the peripheral nervous system, which is everything else. Okay, the only two types of nervous tissue in your body. You're either brain and spinal cord, or you're everything else. We've already talked about brain and spinal cord, so now we're going to start talking about the other nerves in your body. Some basics. This should go back all the way to histology. A neuron is a nerve cell. Okay, that's the most basic unit of the nervous system. Most nerve cells do not directly touch each other. There are some that do, but most do not. The way that they communicate with one another is through chemical messengers called neurotransmitters. This should look familiar. Neuronal anatomy. Okay, we have the dendrites, which receive information. The body, or the soma of the cell, where you have the nucleus and the cytoplasm, all the protein machinery. The axon, which transmits information from one end of the neuron to the other. And finally, the terminal end, which will send a signal on to the next neuron. That's the basic structure of a neuron. The dendrites, the body, the axon, and the terminal end. Processes, okay, are any long extension that allows communications, and you have three types of processes on any neuron. A dendrite, which receives information, an axon, which transmits information, and the axon terminals, which send information. So we have receiving, transmitting, sending from one end of the neuron to another. The soma, the cell body again, that's the nucleus, that's the protein machinery, the ribosomes, all the genetic information, that's all going to be in the soma. The dendrites, very, very highly branched. They are receiving information. One cell can have up to 400,000 dendrites, so nerves are highly, highly connected to one another. When they have more dendrites, they're increasing their surface area, they increase their capacity to receive signals from many other neurons. And that's what makes the brain highly developed. The more connections, the more pathways between the neurons, the easier it is to recall and process information. The axon, or nerve fiber, that's the transmitting process. Okay, it carries information from the dendrites to the terminal end. It can be a few microns, which is 1/1000th of a meter, to over a meter. Okay, there's an axon that has to reach from your spinal cord to your big toe. That's a long axon. Occasionally you will have collaterals, branches off the axon, but that's not always the case. The axon terminal, the very end of the axon, is where the neurotransmitters are housed, and when one neuron needs to communicate with another, after the information has been transmitted from the axon terminals will release the neurotransmitters. And finally, the axon is covered in myelin. Myelin is a type of plasma membrane that covers, insulates, and protects the axon. When we look at myelin, we can divide it into two different types, depending on whether it's found in the central nervous system or the peripheral nervous system. In the central nervous system, the cell type responsible for creating myelin is called an oligodendrocyte. In the peripheral nervous system, the cell type responsible for myelin is called a Schwann cell. When we look at myelin, we notice it's not a continuous sheath around the axon. It actually has spaces in between different sections of myelin, and those spaces are called nodes of Ranvier, and those are going to become very important as we start to talk about the way that neurons work. And here's a picture. We have the oligodendrocyte. Notice that that must be in the central nervous system. And one oligodendrocyte can myelinate more than one axon or more than one spot on an axon at a time. In the peripheral nervous system, you have the Schwann cell. Now, the Schwann cell actually wraps itself around and acts as the myelin. Okay, so this is the Schwann cell and the myelin, unlike in the central nervous system where the oligodendrocyte is responsible. Okay, three functional classes of neurons. And function has to do with what type of information do they relay. Afferent, efferent, and interneurons. Afferent neurons convey information from the body, from the peripheral nervous system, into the central nervous system. And if you look all the way back at the flow chart in the brain and cranial nerve lecture, you'll notice that information that's coming from the body into the central nervous system is only one type. It's sensory information. Efferent neurons go the opposite way. They convey information from the central nervous system into the body. And again, if you consult that flow chart, you'll see that that's one type of information. That's motor information. Sensory information only goes into the central nervous system through an afferent neuron. Motor information comes out of the central nervous system through an efferent neuron. Okay? And we've used this example before. If you think about setting your hand on a hot stove, okay? We set our palm down on the hot stove. Sensory information rushes in, telling us that we are burning our hand, and our brain's reaction is to send motor information out to make you remove your hand off the hot burner. Okay? So classic example of sensory information can go in, motor information can go out. Sensory information goes in through an afferent neuron. Motor information comes out through an efferent neuron. In the spinal cord, in the central nervous system, these two neurons cannot communicate directly, so they have to be connected by interneurons. So interneurons connect afferent and efferent neurons. Here's the picture. The light blue indicates peripheral nervous system. This light green is central. Afferent, notice it's coming from a sensory receptor, comes into the central nervous system. You have interneurons connecting it with an efferent neuron. Notice that its ultimate target is a muscle, a gland, or another neuron. It's going to be providing motor information. Okay, a little bit about neural growth. So nerves begin to grow very early on. That's one of the very first structures you're going to get in embryonic development. In the embryo, the stem cells are going to differentiate into neurons or glial cells. Again, if you go back to histology, we said glial cells are support cells. Okay, neurons make a mess, they need some help, they need help cleaning up. That's the job of a glial cell. Each cell is going to grow and make its final connection due to different inhibitory or growth factors located in the extracellular fluid. So how did that nerve from your spinal cord know how to get to your big toe? It followed a bunch of growth cues in order to make its final destination. Neural regeneration. So when you are born, all the nerve cells you have are all the nerve cells you are ever going to have. That's what being terminally differentiated means. It means you can never get any more nerve cells. If nerves are damaged, they can sometimes repair themselves. But if a nerve cell dies, you can never get that cell back. So if you damage the cell, first of all, it has to be in the peripheral nervous system. Central nerves cannot regenerate themselves. Peripheral nerves have a chance. If a peripheral nerve does regenerate, it's at a very, very slow rate, 1 millimeter per day. One of the big problems with central nervous system injuries is that a lot of times they crush the brain and spinal cord rather than cut it, and what that does is causes cells to undergo something called apoptosis, which is cell suicide. When cells sense they have been damaged, in order to prevent more damage from occurring, frequently cells will kill themselves, which is what apoptosis is. Alright, now into physics. Remember, it's not a coincidence that the word physics and physiology share the same root word. So now we're going to talk about electricity before we talk about nerves. Extracellular fluid, the fluid surrounding a neuron, has mostly positively charged sodium ions and negatively charged chloride ions. Anytime you separate electrical charges, you create the potential to do work. That principle is called electric potential or potential difference. It's based on the fact that opposites attract. Positive and negative charges want to be together. So by separating them, you create the potential to do work. Electric potential is measured in volts. Okay? We're all very familiar with volts. Even batteries are in volts. All a battery is two compartments that are separating charge. If you pick up a battery, you notice that one end is positive, one end is negative. those ions are being separated within that battery, creating electric potential, which you have a 9-volt battery, you have voltage in batteries. When we allow ions to move, okay, if we remove the partition and we allow positive and negative charges to start movement, that's called current. When we hinder or we slow that current down, it's called resistance. Voltage, current, and resistance are all related by something called Ohm's law, and it's I equals V over R. Okay, so current is voltage over resistance, and this comes in handy when we talk about materials that insulate or conduct. Materials that insulate have a high electrical resistance and a low current flow. Materials that conduct have a low resistance and allow for rapid current flow. Okay, so insulating materials have a very high resistance. Conducting materials have a very low resistance. How does this apply to a cell? Okay, in any cell, you have intracellular fluid inside the cell and extracellular fluid outside the cell. Both are mostly water, and the reason that you don't sit in a bathtub with a hairdryer is because water is an incredibly good conductor of electricity. Okay, it works out inside your body, doesn't work out so well if you're sitting in a bathtub with a hairdryer. The lipid bilayer, okay, your phospholipid bilayer is an insulator or a resistor. The resistance is very high. Okay, so under resting conditions, which means the neuron's just sitting there, a difference exists across the lipid bilayer, a separation of charges. Positive charges on one side of the bilayer, negative charges on the other side of the bilayer. That's called resting membrane potential. By convention, something always has to be zero. Okay, we always have to compare something to zero in science. So when we're talking about resting membrane potential, the extracellular fluid is always considered zero. When a cell is at rest, there is an excess of negative charge on the inside of the cell. Okay, the outside is zero, there's lots of negative charge on the inside, so we say that most cells will use an average resting membrane potential of negative 70 millivolts. Okay, that's average resting membrane potential. The magnitude, how negative that charge is, depends on two things: differences in ion concentrations, intracellular and extracellular, and differences in membrane permeability. So if it's negative 70 on the inside and then we start to put more negative ions on the inside, that's the first one. That's an ion concentration. So we could go negative 70, negative 80, negative 90 if we keep piling in negative ions. Membrane permeability means how easy is it for these ions to move back and forth across the membrane. We can pile negative ions inside all day long, but if they can escape through the membrane, it's not doing us any good. So the membrane permeability also comes into play. Here's a picture just illustrating that our extracellular fluid is zero, and if we could put another electrode inside the cell, we would see that there's an excess of negative charge on the inside of the cell during resting membrane potential. Alright, these two panels illustrate the way that ions move across the membrane. If we look in this first panel on the left, notice you have sodium chloride and potassium chloride. What we want to focus on are the sodium and potassium. These red dashes indicate gates that allow potassium to move. Sodium cannot move, okay? Only potassium can move. So when these gates open, potassium is going to want to move from an area of high concentration to an area of low concentration. So potassium immediately starts to flow through its gate. Keeps flowing, keeps flowing. All of a sudden, it's building up on the other side, on the dark blue side. But potassium's not what's building up. Positive charge is building up. Potassium carries a positive charge and sodium carries a positive charge. If opposites attract, like charges repel one another. So as positive charge builds up on the other side, it starts to force potassium back across the membrane into its original compartment. This continues on until an equilibrium is reached, where you have the same amount of potassium going down its concentration gradient as you have flowing back across due to being repelled by a similar charge. And if we look over in this, it's the same example, just using sodium. So the blue gates indicate sodium gates, gates that only sodium can move through, potassium cannot move through. So as we open up the gates, sodium moves down its concentration gradient from an area of high concentration to low concentration. It continues to do so until we get a buildup of positive charge on the opposite side, which sends sodium back to its original compartment. That continues until the amount of sodium flowing down its concentration gradient is equal to the amount of sodium coming back due to being repelled by a like charge. There it is. Okay, I was going to say, I knew I had a slide that had the verbal explanation of the whole thing. So this says when ionic charges build up on one side of the lipid bilayer, an ion can reach equilibrium potential when it moves down its concentration gradient, and that's meant by its desire to be repelled by like charges. There's no more net movement. And that's that panel. Okay, nerve signaling. So nerves have changes in membrane potential. That's how they communicate with each other. Okay, they change from -70 to -80 to -90, maybe into positive numbers. That's how nerves communicate. And communication can occur in two forms, graded potentials and action potentials. Graded potentials are good for short distance signaling, okay? Opening a channel, opening a gate, doing something from here to right over there. That's a graded potential. An action potential is long distance signaling. When we said that information is received through a dendrite, it has to be sent all the way down the axon to the axon terminal. That's going to be an action potential. If you just want to move a little something, open or close a gate, that's a graded potential. So before we can do potentials, we have to do a little vocabulary. And you're going to want to remember this vocabulary all the way through 202, so get it on note cards right away. Depolarize, repolarize, hyperpolarize, and overshoot. Depolarize is when the resting membrane potential, when the potential in the cell is less negative than resting level. Resting level is -70. So if you want to be less negative, that's -60, -50, -40. That's depolarizing. Repolarizing is when membrane potential that has been depolarized returns to its resting value. So if we went from -70 to -40, and then we came back to -70, we'd be repolarizing. Hyperpolarizing is when the potential is more negative. So if we go -70, -80, -90, that's hyperpolarizing. And then finally, overshooting. Overshooting is when the inside of the cell becomes positive relative to the outside. So if we go -70, -60, 50, 40, 30, 10, 20, 10, 0, +10, +20, +30, then we're overshooting. And here's a pictorial representation. The red dotted line is your resting membrane potential at -70. When you become less negative, you depolarize. When the inside of the cell becomes positive, that's overshooting. When you return back to resting membrane potential, that's repolarizing. And then when you go more negative than resting membrane potential, that's hyperpolarizing. So we'll talk about graded potentials in this lecture, action potentials in the next lecture. So graded potentials, again, short distance signaling, confined to a small region of the plasma membrane. Their magnitude can change. That's where you're getting the word graded. And again, they're used for things like opening membrane channels, very short distance signaling. Some other characteristics of graded potentials, they can be depolarizing, they can make the cell less negative, or hyperpolarizing, they can make the cell more negative. They can vary in size, okay, which means they can have different degrees of being depolarizing or hyperpolarizing. They're conducted decrementally, which means as you move away from the point of origin, the signal gets weaker. That's decrementally. And if you can provide an additional stimuli before that potential has died away, it can add to the first stimuli, which is summation. And here are some pictures to illustrate. So we said they can be depolarizing or hyperpolarizing. Okay, they can have different vary in magnitude. So it can be a weak stimulus or a strong stimulus. They're conducted decrementally, which means here's your original, the stimulus site. If we move away 1 millimeter as we get farther away, it becomes smaller. That's what this is as well. This is conducted decrementally. As you move away from the site of initiation, the signal becomes weaker. Again, when we talk about summation, which is the only thing not depicted here, if we could add another depolarization, say right in the middle, that would be summation. We could boost the magnitude of this particular signal. I feel like I have another slide. I guess I don't. So that's graded potential. Action potentials are the big one. We'll do that in the next lecture.